Okay, I can't believe it's not homogeneous poisson. So most current hypotheses about neural computation use the concept of firing rate. And traditionally, firing rate is defined as the average number of spikes over repeated trials under the same experimental condition. So it's attributing any trial-to-trial variability entirely to irregular spike generation. Okay, studying the mean firing rate of neuron across various brain areas has provided valuable insight into the sensory motor system and mechanism of perceptual decision making, and much more. For example, if you look at some neurons in LIP, they show gradual ramping during sensory decision making, which usually interpreted as gradual evidence accumulation. But mean firing rate in many cases cannot distinguish between possible competing hypotheses. For example, there is a debate over whether single trial LIP spike train are better described by discrete stepping or continuous ramping dynamic. And mean firing rate is not really useful here, yes? Because since both these hypotheses could produce the same mean firing rate. Fortunately, in the past decades, we have seen the development of many wonderful methods for the inference of single trial firing rate. And what most of them, I would not say all, but what most of them have in common is their reliance on inhomogeneous Poisson assumption as the spike generation mechanism. Before we go further, I'd like to quickly go over the definition and properties of homogeneous and inhomogeneous Poisson process. Spike variability generally arises from two sources. One is firing rate variability, and the other one is spiking irregularity, that is because of the point process. In the homogeneous Poisson process, firing rate variability is zero, because firing rate is constant. So the variability, so it's all spiking irregularity. Now, there are two common metrics that people use to measure spiking irregularity. First is just the Fana factor, which is defined as the ratio of variance of the number of spikes that we see over trials divided by E of n. And Fana factor for the homogeneous Poisson process is 1. The other is just coefficient of variation squared for spiking irregularity, which is defined as the square ratio of standard deviation of ISI divided by mean. And again, for the process, Poisson process, this is 1. Okay, what is inhomogeneous Poisson process? One way to define homogeneous Poisson process is just through generative definition. We could define it by just one stochastic process, lambda t, that generates a single trial firing rate and 3-step algorithm for generating spikes. In the first step, using the lambda process, we generate like single trial firing rate. Here I show one realization of data by green and other realization by gray. In the second step, we generate spike from homogeneous Poisson process with firing rate of 1 Hertz. But this spike is in operational time, so it's not real time. And in the third step, we map the spike from the operational time to a real time by squeezing and stretching time in a way using the firing rate that we find that make sure that the instantaneous firing rate in the real time is actually exactly the same firing rate that we generate. Okay. However, the spiking of neurons across many brain areas deviates significantly from inhomogeneous Poisson process. Payman and Rassa found that in a really great article in 2009 found that many neurons in area 5 and LIP spike remarkably regular, like a clock. Later, all other people also observed that the similar finding made basically in various brain area. So here, if you look at the numbers, it should be 1 again to be critical Poisson. But in many higher order motor, you see sub-Poisson behavior, and many visual area and prefrontal, you see like super Poisson. Okay. But why we should care? That's the question. In an insightful article, our beloved Jan demonstrated that the consequence of incorrect spiking assumption on a model selection is really important. So he applied drift diffusion model with sub-Poisson spiking. So this is basically generate synthetic data. So we have drift diffusion model, sub-Poisson spiking, but we incorrectly assume that we have inhomogeneous Poisson spiking, and we attempt to identify the best model to explain the data. Okay, and two hypotheses, stepping or wrapping. And we observe that here a negative DIC means that we're basically DDM, and being close to zero, it means that we are stepping. And what we observe is just when we actually make the synthetic data be more like irregular, then incorrectly the best model will be stepping. So it's really important to make correct assumption about like the spike generation mechanism to make sure that the single trial inference, because all the hypotheses that we want to test is based on this dynamic of single trial. So we want to make sure that we correctly do that. So okay, in the rest of my talk will be in like four parts. First, I introduce an alternative, which I call double stochastic renewal framework. I try to validate this framework to make sure that it works. And then I do a survey of spiking irregularity in the cortex. And at the end, I try to come up with a network mechanism that explains the spiking irregularity that I observe. Okay. What is the double stochastic process? The double stochastic process is a pair, here shown by G, a renewal distribution, and a lambda, which is a stochastic process for a single trial firing rate, and three-step algorithm to generate the spike, similar to inhomogeneous process. In the first step, we use lambda to generate single trial firing rate, which here is shown by green curve. In the second step, we use this renewal distribution G to generate inter-spike interval. But we choose the mean of this G to be 1. That makes sure that the firing rate in this operational time is 1 hertz. It's similar, but we are basically focusing on inter-spike interval this time. And we use this same map that squeeze in the stretch time to make sure that the instantaneous firing rate is correct. Okay. We pick this G distribution to be gamma distribution because gamma distribution has been proven to be really useful for modeling ISI distribution, and it's also an extension of exponential distributions. Exponential distribution is a particle case of this, which help us to actually go beyond Poisson. Since gamma distribution has 2 free parameters, and if you remember, we set the mean of the G to be 1. So basically we are left with 1 parameter, standard deviation. We could play with this and similarly define the CV2 of this distribution, which is sigma 2 divided by mu2 as our free parameter, which we call the spiking irregularity. So as a result, I could interchangeably use like this phi quantity, which is spiking irregularity, or renewal distribution. There's a one-to-one mapping. Okay, here we see like 4 examples of this gamma distribution. For phi equal less than 1 means that phi less than 1 means like sub-Poisson distribution. Phi larger than 1 is just super Poisson distribution. And you could parameterize it just by 1 parameter. Okay, now the question is, okay, we define this model, how should we infer it? Okay, let us assume that the single trial firing rate is approximately constant over some time scale tau. So basically we are here assuming that there is not, there is a time scale that we don't see jumps. So that's an assumption, that's a constraint. Then if we choose the bin size t to be smaller than tau, we can partition the overall trial variance of the number of spikes in 2 parts. One is just firing rate variance, the other one is point process variance. Great. Now if we do assume that this point process comes from double stochastic renewal process, if we assume that we have some constraint with mean size, and if we assume that G is gamma distribution with like several pages of calculation, we could come up with this analytical form. So here we still don't have access to P. E of n is really easy to read from data. E of n also is really easy to read from the data, but values of lambda t we don't know. So the trick is just to look at 2 different time scales And by looking at the two different time scales and assuming that the fine rate changed continuously, we could actually solve this equation. And we could uniquely determine phi. Okay, but let's test this. To test this, we consider two classes of stochastic processes for the lambda. One, for the upper one, the lambda is constant in time, but we see a variability from trial to trial. In the second one, we have a drift diffusion with sticky boundary. We generate synthetic data from this, which we know the ground truth, and we generate with possible large range of phi. So we tested an estimated phi, which with the method that I mentioned is really close to the ground truth. But this is indirect. I only have access to spikes. And I know the ground truth and I test it. Good, but can I have directly test the underlying assumption? Okay, we can, but we need a single trial fine rate, which we don't have. Yes? But if from somewhere, let's say, we have access to the single trial fine rate, what we can do is just we can use the reverse of the spike generation process, map this spike in real time by using this map to the operational time, and then calculate the CV2 of this in operational time. So basically, removing the effect of fine rate. But this needs to have access to the single trial fine rate. So, okay, the trick is here, is just we use intracellular recording of membrane potential from neurons in the battery cortex of awake mice to estimate the single trial fine rate. So what we do is just first we remove the action potential from this membrane potential, then we bin it, and then by binning it we find basically what is the relation between membrane potential and the number of spikes in that bin, so which here shows by this dotted blue. And average over the data points with 1 millivolt voltage, we find this relation that people already observed for the past 10 years. Okay. Now that we have access using this member tray, now we basically estimate the single trial fine rate, and using this estimated single trial fine rate, we may estimate the spike in irregularity. If we do that, which here shown by the blue, and then phi shown estimated by our method, is really close, like 20% error at most of some cases. Okay, on average, on some cases. Okay, now we have this method, and it seems it works. So I applied it to like many cortex in many different areas. The area is spanning like different stages of cortical hierarchies, from sensory V4 to association LIP and premotor area PMD. The figure on left shows the distribution of spiking irregularity across different cortical area, and here what we see is the diversity. Like we see that many regular neurons in LIP and PMD. We also see many super Poisson neurons in V4. So, and like some particular neuron behave like Poisson, but not all of them. We also see that the diversity of neuron in V4 is much larger than PMD and then LIP and then PMD. Okay. Then we could look at this trade graph on the right, show like how the fine rate of the neuron is related to the spiking irregularity. And if this red dashed line and gray dashed line show the 7% quantile, and what we notice is just in the upper right, basically is empty. So there is no high firing rate neuron, which could be irregular. Okay, and another important consideration, if we want to actually use double stochastic renewal process, is whether this spiking irregularity in neuron change dynamically. So if it change from condition to condition or change in time, so we check that. We look at the Wien for neuron in the spatial attention task performed by a monkey. When we observe the spiking irregularity is completely invariant under attention condition. Then we analyze PMD neurons in decision-making tasks performed by the monkey. We observe the spiking irregularity of LIP neurons invariant for, PMD neurons invariant for difficulty of the task or the choice. This also was true for LIP. Okay. This is not like, can we assume that it's completely invariant? The answer is no. The result shows that, for example, if we look at fixation epoch and decision epoch, so pre-stimulus and then making decision epoch, there is a significant increase in spiking irregularity during decision making, but the effect is small. Okay, I observed like 3 properties of spiking irregularity. One is diverse spiking irregularity. The other one is anti-correlation between firing and spiking irregularity. And the third one is nearly constant. It's nearly constant under many conditions, but can also change with the network state. Can I come up with the network mechanism that actually explain this to you? So here we use like spiking recurrent neural network. First, I think you use spiking 1. The model already could explain several characteristics of spiking variability in V4, I think. And the model is a 2-dimensional balanced network of excitatory inhibitory neuron. There's like 2 layers. The first is just V4 layer Poisson neurons. And the thing is just, the special thing about this is just we have spatially ordered connectivity. So the chance that you can make a connection is just much more with your neighborhood. Okay, so basically if we look at the spiking irregularity of this neuron, we see the diversity, we see that the feed falls off with the fine rate. So all these excitatory and inhibitory neuron is just completely deterministic. Yes? So we have this deterministic ODE coupled together. So the diverse and all these neuron are like basically have the same parameters. They're not really different. So why some of them have like different spiking irregularity? So basically the diversity should be related to how neurons were embedded in the network. So the connection between neurons in the network is just a model are made randomly with distant independent probability. So by chance, some neurons receive more excitation than inhibition. And as a result, they reside near or maybe above threshold. And so as a result, as figure shows, spiking irregularity decrease with the balance in the total number of excited inhibitory connection received by neuron. So consistent with this, spiking irregularity neuron is also negatively correlated with the average finder. Okay, at last what we observe is if we basically change the input driven, change the input over the operating regime, we observe that the neuron we can produce modulation of spiking irregularity. Basically, by increasing the mu x, we could actually increase fine rate and decrease life. But in PMV area, we observe that both spiking irregularity and fire rate increase. So how could we explain that? We basically observe by simultaneously changing the membrane conductance and membrane input, we could actually produce that. Okay, in conclusion, DRC is a flexible mathematical model for partitioning spiking variability. Cortical neuron shows a wide range of spiking irregularity, which is invariant in many conditions. And if spiking irregularity can come from a network dynamic and neurons embedding with the network and is compatible with the deterministic voltage threshold model. And latent variable model needs to incorporate in non-Poisson spiking irregularity. At the end, I want to mention there are like several papers that go beyond Poisson, but it's good to see more of this. They take different approach than us, but I love to see more of this. Thank you guys.